We're going deep into the inner ear. This is an organ that's it's essentially a self-contained, high-fidelity biological gyroscope and sound analyzer all rolled into one.
This dense sensory apparatus, and it's located entirely within the petrous temporal bone.
Which is one of the hardest bones in the entire body.
It is, for a very good reason. So our mission today is to really navigate its three distinct but deeply intertwined functional systems. We want to understand not just the big picture, the structure, but the exotic physics and, the strange chemistry that lets it all function at a level of sensitivity that it's almost unimaginable.
Okay, so what are those three areas?
Specifically, we're targeting three major functions. First, the cochlear organ, that's for hearing. It's designed to convert fluid dynamics into pitch and volume.
Right.
Second, you've got the utricle and saccule. These handle your static position relative to gravity and linear acceleration.
So like my sense of up and down or moving in a straight line in a car.
Exactly. And third, the three semicircular canals. These are dedicated solely to registering angular acceleration. So head rotation, spinning, all of that.
And the whole system, which is encased in this incredibly dense bony shield, it relies on just two things, right?
Fundamentally, yes. Highly specialized fluid dynamics.
Okay.
And these unbelievably delicate sensory cells, which we just call hair cells.
Right. So we're going to look at the protective bone, the almost unbelievable ionic chemistry that creates this massive internal electrical current.
A huge current.
And the incredible micromechanics that turn physical movement. And this is the part that blows my movement smaller than a single hydrogen atom into a stable, reliable electrical signal for the brain.
It's a marvel. It's a perfect example of convergent evolution. It's using the same basic sensor, the hair cell, to do two completely different jobs.
We have to start with the shell. I mean, the inner ear is always described as delicate, but the structure protecting it is anything but.
Absolutely.
We'll start with the osseous or bony labyrinth. It's this dense, hard casing, a series of interconnected cavities carved right into the petrous temporal bone, and it's filled with the fluid perilymph. So why? Why is this dense bone within a bone protection so absolutely crucial?
Well, that density is really the first layer of quality control. The structures inside the inner ear, they're essentially floating. They're suspended by this really fine connective tissue.
Okay.
Now, if the bone around them was susceptible to vibration or, trauma, the sensory parts would constantly be feeding distorted or just damaged signals to the brain.
It'd be like trying to listen to a record on a vibrating table. Just noise.
Exactly. Pure noise. Because the petrous temporal bone is so dense and resilient, it provides this incredibly stable, shock-resistant environment. And the bony labyrinth itself, we can divide it into three parts that house the actual organs.
Right.
There's a central connecting piece, the vestibule, then the rotational sensors, the bony semicircular canals, and finally the auditory analyzer, the cochlea.
Okay, let's start in the middle then. The vestibule. This is the central hub. Anatomically, it's situated medial to the middle ear cavity, the tympanic cavity.
Yeah.
And it acts as this crucial connection point. Sits behind the cochlea and in front of the semicircular canals.
It truly is the lobby of the inner ear. It's the central station. Internally, the vestibule contains the two primary sacs of the membranous labyrinth that are dedicated to linear balance.
The utricle and the saccule.
That's them. But functionally, the vestibule's most critical architectural role is linking the inner ear back to the middle ear, and it does that through two very famous openings, the windows.
The input and the output, right?
Precisely. First, you have the oval window. This is the input port. It's closed off by the footplate of the stapes.
The little stirrup-shaped bone.
That's the one. It transmits the amplified vibration from the middle ear. So the vibration of the stapes right here is what starts the pressure wave in the paralymphatic fluid.
Okay, so that's the in. What's the out?
The out, and this is equally important, is the round window. This one is closed by something called the secondary tympanic membrane.
Wait a second. So if the inner ear is filled with fluid, paralymph, and fluid is almost perfectly incompressible, what happens when the stapes pushes inward at the oval window? Where does the fluid go?
That is a fantastic question. And it gets to a fundamental physics principle at work here. Since the fluid is incompressible for the states to push in and create a wave, something else must move outward to equalize that pressure.
So the round window is the pressure relief valve.
It is the necessary pressure relief valve. Its membrane bulges outwards into the middle ear just to accommodate that minuscule inward displacement of fluid. If the round window were blocked or if it stiffened up,
The whole system would lock up.
it would lock up. The hydraulic system would fail, the basilar membrane couldn't oscillate, and you'd get immediate conductive hearing loss.
Wow. So the round window is what ensures that this tiny atomic level movement of the stapes can actually translate into fluid waves that travel down the cochlea. That's a fascinating and an absolutely required piece of architecture.
It is, and we find another interesting piece extending from this central hub, the vestibular aqueduct.
Okay, what's that?
It's this small canal that runs back and vertically through the bone. It eventually leads to the endolymphatic duct and sac.
And the sac itself, where does that end up?
The sac is a blind pouch that actually resides within the protective layers of the dura mater.
The tough outer membrane covering the brain.
Exactly. And this whole duct and sac system is absolutely crucial. It regulates the volume and the chemical composition of the endolymphatic fluid. It's probably the main site for fluid reabsorption and waste removal for the inner ear.
Okay, so moving from that central vestibule, let's go posteriorly. We hit the bony semicircular canals, the original biological gyroscopes.
That's a great way to put it.
There are 3 of them.
Yeah.
The superior or anterior canal, the posterior canal, and the lateral or horizontal canal.
And the absolute genius of these structures lies entirely in their geometry. It's all about the angles.
How so?
They are arranged at strict right angles to each other. Think of the 3 axes, X, Y, and Z, that define 3-dimensional space.
Okay, so they're perfectly perpendicular.
Perfectly perpendicular. And this precise arrangement guarantees that no matter how complex the rotational movement of your head is, whether you're tilting forward, that's pitch, or rolling sideways, which is roll, or turning left and right, that movement will always create a maximum flow differential in at least one of those canals.
So it can capture any possible rotation.
Any possible rotation. And structurally, they're incredibly efficient. They aren't even full circles. The sources describe them as roughly 2/3 of an arc.
And they vary in size a bit.
They do. The superior canal is quite long, around 15 to 20 millimeters. The lateral canal is a bit shorter, maybe 12 to 15 millimeters.
And at one end of each of these canals, we find the specialized sensory structure housed in a swelling called the ampulla.
Yes, the ampulla.
Yeah.
And this swelling is almost double the diameter of the rest of the canal. This enlarged area is where the sensory cells reside, just waiting to detect the flow of fluid. You can think of the ampulla as, I don't know, like the carburetor bowl for the flow sensor mechanism inside.
Now, here's where it gets really insightful, I think, in terms of function. The canals don't work in isolation. They're a cooperative pair across the body.
Yes. The semicircular canals are functionally paired across the 2 ears. This is vital for accuracy.
So give me an example. What happens when I turn my head to the right?
Okay, so when you turn your head to the right, the horizontal canal in your right ear experiences maximum fluid movement in the excitatory direction.
So it's firing more.
It's firing more. At the same time, the horizontal canal in your left ear experiences movement in the inhibitory direction.
So it's firing less.
Exactly. So the brain isn't just relying on a single yes signal. It's constantly calculating the difference between the left and right signals. This is called push-pull signaling.
So it's always comparing.
Always comparing. And furthermore, the superior canal in one ear is typically coplanar and functionally linked with the posterior canal in the opposite ear. This whole setup just maximizes sensitivity across all rotational planes at the same time.
So my brain is constantly doing vector analysis and differential equations on this incoming data stream just to keep me from falling over. It's always comparing left versus right to determine the exact movement, not just that there is movement.
That's precisely it. This dual ear sensing allows for this rapid, highly accurate comparison of signals, which is necessary for the lightning-fast motor reflexes we need to maintain our gaze and our balance. It's a highly optimized biological inertial measurement unit.
Incredible. Okay, now let's spiral forward from the balance system to the cochlea, the part of the bony labyrinth dedicated to sound. And it looks exactly like a snail shell. It's a beautiful piece of natural engineering.
It's a coiled masterpiece, absolutely. It's geometry. The cochlea spirals about 2 5/8, turns around a central bony core. That core is called the modiolus.
And the modiolus is important in its own right, isn't it?
Very important. It's functionally critical because it houses the primary nerve cell bodies for hearing. That's the spiral ganglion of the cochlear nerve. The entire structure, though, is surprisingly small. It measures only about 9 millimeters from its base to its apex.
So this tiny coiled structure is responsible for taking all the sound frequency information in the world and mapping it out in physical space. How is that space internally partitioned to do that?
That mapping relies completely on the internal architecture. Running up the entire spiral from that central modiolus is a bony shelf called the osseous spiral lamina.
Okay.
And this shelf partially divides the internal cochlear canal. This division sets the stage for the three channels, or scalae, that will eventually form. In the bony labyrinth, it separates the space into the superior channel, the scala vestibuli, and the inferior channel, the scala tympani.
And both of those are filled with perilymph, that normal extracellular fluid. And they run parallel, but they don't mix until the very top. Is that right?
That's exactly right. Along their entire spiral length, they are separated. They only communicate at the very apex through a tiny little opening called the helicotrema.
Helicotrema.
Yeah. So sound waves traveling up the scala vestibuli have to use this apical pathway to then return down the scala tympani. And this long travel path is what ensures the pressure wave has enough time to dissipate its energy into the middle structure, the part that actually hears the sound.
And structurally, just to connect it back to the middle ear again, the scala vestibuli connects to the vestibule of the oval window. That's where the stapes pushes the fluid in. And the scala tympani ends at the round window, providing that essential pressure relief we were just talking about.
Correct. The entire bony labyrinth is just this carefully structured hydraulic system designed to protect and then propagate these very specific fluid waves.
So we've established the rigid protective bone architecture. Now let's go inside the engine itself, the membranous labyrinth. This smaller, much more delicate system is floating inside the bony labyrinth, suspended by connective tissue. And critically, it maintains two wildly different fluid environments right next to each other.
This is where the biological complexity it explodes. The entire function of the inner ear, all of hearing and all of balance, is predicated on the success of maintaining a massive non-equilibrium difference in the ionic concentration between these two fluids.
And if that chemical barrier fails,
the entire sensory system stops working instantly.
Wow. Okay, so the membranous labyrinth is basically a refined, smaller system of sacs and ducts that follows the general spiral shape of the bony labyrinth.
Precisely. It consists of the vestibular apparatus, that's the utricle, the saccule, and the three semicircular ducts, and the cochlear duct, which is also called the scala media. And this entire membranous system is filled with a completely different fluid, endolymph.
And tying the vestibular part of it all together is the endolymphatic duct and sac. We mentioned its location in the dura mater, but what's its functional significance beyond just drainage?
The integrity of this entire sensory system hinges on fluid homeostasis. The sac sits there in the dura mater, and its lining contains these highly specialized complex cells with microvilli, which are key to reabsorption.
So it's like a sponge.
It's an active sponge, yeah.
Yep.
The endolymphatic sac is widely believed to be the primary area where this endolymph is reabsorbed back into the venous system, regulating the volume. But more than that, the specialized cells are known to engage in processes like phagocytosis.
Meaning they eat debris.
They eat debris, they're active in clearing out junk, and potentially participating in the local immune surveillance of the inner ear. And dysfunction here, leading to poor drainage and fluid buildup, that is the central mechanism of devastating balance disorders like Meniere's disease.
Let's talk chemistry, because you said this is where the system gets its power. We have two fluids, perilymph and endolymph, separated by those delicate membranes. Let's start with perilymph, which fills the bony channels, the scala vestibuli and scala tympani.
Perilymph is biochemically pretty ordinary. It resembles typical extracellular fluid or even cerebrospinal fluid, CSF.
So salty.
Very salty. It's characterized by high concentrations of sodium ions, Na+A, and low concentrations of potassium ions, K+A pale. Our source materials define this as roughly 150 millimolar Na+, and only about 5 millimolar K+A. It's the standard watery environment you'd find around most cells in your body.
Okay, that's the baseline. Then we cross the membrane and find endolymph, which is chemically inverted.
It is chemically extraordinary. Endolymph fills all the internal membranous spaces, and it is uniquely similar to intracellular fluid, meaning it is dramatically high in potassium, around 120 millimolar K plus Sut.
And the sodium?
Extremely low in sodium, only about 1 to 2 millimolar Na plus cerium. It's a complete chemical flip.
Wait, hold on. Potassium, K plus uri, is usually high inside the cell and low outside. That's what helps maintain the cell's negative charge. Doesn't having high external K plus completely flip the standard model for how a neuron or a sensory cell should fire? How does the hair cell not just fire constantly?
That is the essential insight. That's the beautiful, weird part of this system. In every other sensory neuron, the external fluid is high in sodium, and when the cell is stimulated, sodium rushes in to cause depolarization.
Right.
Here, the hair cells are bathed in this potassium-rich endolymph. The high K+ concentration outside the apical tip of the hair cell means that when the mechanical channels open, K+ immediately rushes into the cell because of the concentration gradient.
Ah, so K plus is the ion that carries the current in, not sodium.
Yes. This is the mechanism of mechanical electrical transduction that is unique to the inner ear. If the external fluid were low in K+ nonol, the system would fail completely.
And this leads us to something called the endocochlear potential, or ECP. This isn't just a chemical gradient, it's a massive active electrical charge that supercharges the whole system. This is where it gets really, really interesting.
The ECP is one of the most astonishing electrical phenomena in the entire mammalian body. It's created because a specific tissue, the stria vascularis, is actively pumping positive K+ ions into the endolymph.
So it's creating a battery.
It is creating a biological battery. This makes the endolymphatic fluid approximately plus 80 millivolts, plus 80, relative to the perilymph and the basal portion of the hair cells. Now remember, the hair cell interior maintains a normal negative resting potential of about minus 70 millivolts.
So you've got plus 80 millivolts bathing the top of the cell and minus 70 millivolts inside the cell. That means there's a staggering 150 millivolt electrical driving force across a single microscopic membrane.
Exactly. This enormous potential difference, nearly 150 millivolts, acts as a pre-charged battery. This massive electrical pressure is what drives the K+ ions into the hair cell the instant those mechanical gates open. And this enormous driving force is why the hair cells are so incredibly sensitive. They can respond to movements smaller than the diameter of a hydrogen atom. It is the bioelectrical power source of hearing and balance.
So the maintenance of that 150 millivolt ECP requires a constant, highly metabolic power source, and that is the stria vascularis.
The stria vascularis is an unparalleled piece of tissue. It's located on the lateral wall of the cochlear duct. It's highly vascularized, almost like a specialized little kidney right there in the inner ear, and it's dedicated to maintaining this ionic balance.
How does it work?
It has 3 layers of cells, marginal, intermediate, and basal cells, all working in this complex coordination, primarily to pump K+ ions against a massive gradient into the endolymph. It is the metabolic engine of the cochlea.
But this sophisticated high-energy system, that's also its biggest vulnerability, isn't it?
Absolutely. Because it is so metabolically active and requires such a stable blood supply from the labyrinthine artery, it's highly susceptible to any systemic stress. Lack of oxygen, hypoxia, or any disruption of the vascular supply immediately compromises this tissue. And this is precisely where certain ototoxic drugs exert their damaging effect.
Can you give us a concrete example? How do drugs exploit this vulnerability?
Certainly. Drugs like aminoglycoside antibiotics, they're potent medications, but unfortunately, they can be toxic to the inner ear. They are thought to primarily target the stria vascularis.
Wow.
These drugs can interfere with the function of the transport mechanisms, or they can directly damage the cell layers that are responsible for K+ secretion. When the stria vascularis is compromised, that plus 80 millivolt ECP, it drops precipitously, maybe down to plus 20 millivolts or even lower.
And the hair cells instantly lose their 150 millivolt driving force.
They lose their power source. Their incredible sensitivity vanishes, leading rapidly to permanent sensorineural hearing loss. Understanding the stria vascularis is understanding the energy limits of the ear.
So if we connect this to the bigger picture, the vestibular system it's like our sixth sense. It gives us our internal map of orientation, tells us where down is, whether we're rotating or accelerating. And this complexity is handled by 2 main sets of receptors. The maculae, which sense linear motion, and the cristae, which sense rotational motion.
The elegance of the vestibular system is really in its redundancy and its spatial organization. The sensory cells are arranged in these precise planes within the moan, ensuring that the brain receives this comprehensive and continuous stream of differential signals from the paired structures in both ears.
Okay, so let's break that down. The maculae. These are patches of sensory tissue located within the utricle and the saccule, and they're responsible for detecting static position relative to gravity and the forces of linear acceleration.
Right. And it's important to understand the division of labor here. The utricle contains a macula that's oriented largely in the horizontal plane.
Okay.
Therefore, it's most sensitive to movements that are parallel to the ground, like accelerating or braking in a car or tilting your head from shoulder to shoulder.
And the saccule.
The saccule contains a macula oriented mostly in the vertical or sagittal plane. So this one detects motion in the vertical direction, like riding up or down in an elevator or nodding your head forward and backward.
So what are the key components of this sensory patch that
Yeah.
makes it gravity sensitive? How does it feel weight?
The maculae contain the sensory hair cells. There are type 1, which are flask-shaped, and type 2, which are cylindrical supported by surrounding cells. Overlying these hair cells is a thick, flexible, gelatinous layer. This is called the otolithic membrane.
Right.
And crucially, this membrane is weighted down by dense, microscopic calcium carbonate crystals called otoconia, or sometimes statoconia.
So if we use an analogy, the otoconia are the mass element. They're the weight.
Exactly. Think of the macula like a sheet of rubber, that's the otolithic membrane, anchored to a firm surface, the hair cell base. And you've glued fine grains of dense sand, the otoconia, onto that rubber.
Okay, I can picture that.
When you tilt your head, gravity pulls on the heavy sand mass, which drags the underlying rubber. That creates a shearing force that bends the hairs embedded in it. This mass creates the necessary inertia and gravitational pull.
Now let's define the hair cell itself, specifically the role of the kinocilium.
Every hair cell has one single, tall, true cilium called the kinocilium, and then a bundle of stereocilia arranged in a V or a W pattern. The stereocilia are highly organized. They're graded in height systematically, getting taller as they approach the kinocilium.
It establishes an absolute axis of polarity. It's like a biological arrow telling the cell which direction means on and which means off.
It's the arrow. Exactly.
Yeah.
So how does this inertia turn into a signal? The mechanism of action relies entirely on that shearing force. When the heavy otolithic membrane shifts, the shearing force deflects the hair bundles, and the direction of that deflection dictates the output. Movement of the stereocilia towards the tall kinocilium that stretches the mechanical links connecting them, which pulls open the K+ channels.
And thanks to our 150 millivolt ECP, K+ rushes in.
Causing depolarization, excitation. This increases the firing rate of the associated nerve fiber.
And movement the other way.
Movement away from the kinocilium relaxes those links. It closes the channels, causing hyperpolarization and a decrease in the firing rate.
So this means the system isn't just off, waiting for a movement to start firing. It's always firing at some baseline rate. It signals motion by changing its frequency of discharge.
That's absolutely critical for instantaneous feedback. It's the change in the rate of discharge that signals motion. And because the maculae in the left and right ears are oriented in opposite directions, tilting your head to the right excites the right macula while inhibiting the left one. This differential signaling is incredibly precise, and it feeds directly into our immediate reflexes.
Okay, so that's linear motion. Let's switch to rotation, the semicircular ducts. They're located inside the bony canals and are specialized to sense angular acceleration, the turning and spinning of the head.
The structure changes slightly here. It emphasizes flow detection over gravity detection. So inside the ampulla of each duct, we find the sensory ridge called the ampullary crest, or crista, which is where the hair cells are mounted. And these hair cells follow the exact same kinocilium polarity rule as the maculae.
But instead of a heavy otolithic membrane, they're covered by the cupula.
Right. The cupula is a large gelatinous mass that is lighter than the otolithic membrane. It extends fully from the crista all the way to the roof of the ampulla. It acts precisely like a flow sensor or like a hinged door. The hair bundles are completely embedded within this mass.
So tell us how rotation generates a signal here, using that same principle of inertia.
When you begin to rotate your head, the bony canal and the cupula attached to it move immediately. But the endolymph fluid inside the duct initially remains still. It lags behind due to its own inertia.
Right, the fluid stays put for a second.
It does. And this difference in momentum causes the fluid to effectively flow against the cupula, pushing it and deflecting the embedded hair bundles. This deflection stretches the tip links, causes that K+ current to influx, and signals the rotation to the brain.
And what if I stop spinning suddenly? That dizzy feeling.
When you abruptly stop rotating, the bony canal and the cupula stop. But now, the endolymph fluid has its own momentum, and it continues to flow briefly in the direction you were spinning.
So it overshoots.
It overshoots. This residual flow pushes the cupula in the opposite direction. The brain interprets this compensatory deflection as movement, which causes that temporary illusion of motion, the spinning sensation, vertigo, until the fluid finally catches up and settles down.
The information from these sensors has to be immediately applied to our motor system. Otherwise, we'd fall over or our vision would blur. This is the application phase, right?
Yes. And the primary, most well-known reflex is the vestibulocular reflex, or VOR. This reflex is absolutely fundamental to human stability.
So what is the VOR's core function?
The VOR ensures that your gaze remains stable and fixed on an object even when your head is moving rapidly. The vestibular nuclei get the head movement signals and immediately send precise motor commands to the nuclei of the eye muscles. That's cranial nerves 3, 4, and 6.
So if my head rotates 30 degrees to the right,
Your eyes simultaneously rotate 30 degrees to the left without you having to consciously think about it at all.
I know the VOR is so reliable it's actually used diagnostically. Our sources mentioned something called caloric testing. How does that work to test this reflex?
Caloric testing is a really remarkable clinical tool that exploits the physics of the semicircular canals. If you introduce warm or cold water into the external ear canal, it changes the temperature of the nearby endolymph fluid.
Okay.
This temperature change causes convection currents, so fluid movement within the semicircular ducts, even if the person's head is perfectly still.
So you're creating a fake rotation signal.
You're tricking the system. The system interprets this induced movement as a real rotation, and it triggers a predictable involuntary eye movement called nystagmus. By observing the direction and the strength of that nystagmus, clinicians can assess the functional health of the VOR pathway and all the nerve connections to the brainstem.
You're essentially tricking the internal gyroscope with heat to see if the central processor responds correctly. Incredible. So beyond the eyes, what about the rest of the body?
That's handled by the vestibulospinal and vestibulocerebellar reflexes. Signals project extensively to the cerebellum via the inferior cerebellar peduncle, where balance information is integrated with proprioceptive input from your muscles and joints.
So it's combining data streams.
It's combining everything, and it also projects directly down the spinal cord. The vestibulospinal reflexes are what kick in without any conscious thought to brace your posture when you slip on ice. It uses the immediate signal from your head movement to adjust your trunk and your limbs for stabilization. This network ensures your body posture is maintained correctly relative to your head position.
Okay, now we make the fundamental switch from gravity and movement to sound. We're moving into the anterior spiraling part of the inner ear, the cochlea. The mechanics here are all about taking those amplified air pressure waves from the middle ear, translating them into fluid dynamics, and then analyzing them by frequency.
It's amazing. The auditory system uses the same basic hydraulic infrastructure and the same hair cell technology, but it repurposes it entirely for spectral analysis.
We established that the bony cochlea has the two paralymph channels, the scala vestibuli, SV, and the scala tympani, ST. But the functional core is that middle channel.
That's the cochlear duct, or the scala media, SM. This is the endolymph-filled chamber that contains the organ of Corti. It's a triangular space sandwiched between the SV and the ST. And the integrity of this duct depends on three crucial membranes that maintain its shape and that critical ionic barrier.
What are those three membranes?
First, you have Reisner's membrane. It separates the scala media from the scala vestibuli. It is thin, it is delicate, and its entire functional purpose is to maintain that massive ionic difference, that 150 millivolt battery between the potassium-rich endolymph in the SM and the sodium-rich paralymph in the SV.
Okay, so that's the barrier on top.
That's the barrier on top. Then on the bottom, you have the basilar membrane. This is structurally much tougher. It separates the scala media from the scala tympani. This membrane is the key mechanical element that actually oscillates in response to the sound waves.
The third membrane.
The third is the tectorial membrane. This is a passive gelatinous ribbon that projects over the top of the hair cells. It just sits there, waiting.
And on top of that basilar membrane sits the organ of Corti. This is the sensory epithelium, and it's incredibly complex, not just the hair cells themselves, but a whole assembly of comporting structures.
It is the ultimate biological microphone, and the sensory cells are divided into two distinct functional classes, which really emphasizes the differential role of signal transmission versus active mechanical tuning.
Okay, so what are the two types?
First, you have the inner hair cells, or IHCs. They are arranged in a single precise row, about 3,500 of them total. They're flask-shaped, and they are the unequivocal primary auditory receptors.
Primary, meaning they do most of the work.
They do almost all of the sending. They receive an astonishing 90 to 95% of all afferent nerve endings. They are the actual signal transmitters.
Yeah, the second type.
The outer hair cells, or OHCs, these are arranged in 3 to 4 parallel rows, about 12,000 of them, and they're cylindrical. But unlike the IHCs, the OHCs primarily receive efferent innervation.
Efferent meaning motor, or descending signals from the brain.
Exactly. They act as the cochlea's internal motor.
So the inner hair cells are the listeners, and the outer hair cells are the mechanical amplifiers and tuners.
That is the perfect distinction. And the supporting cells are necessary just to maintain this incredibly precise alignment. You have pillar cells, inner and outer, which are rigid, frame-like structures that form the central tunnel of Corti.
Giving it stiffness.
Giving it mechanical stiffness, yes. Then you have diator cells, which are specialized to cradle the OHCs, and their processes extend up to stabilize the whole hair bundle array. The entire complex is structurally optimized for minute, high-frequency vibration.
So a pressure wave enters via the oval window, traveling in the perilymph. How does that wave translate into the sensation of pitch?
The sound vibration, transmitted from the stapes, creates a pressure wave in the scala vestibulae. Since the fluid is incompressible, this pressure wave causes a displacement wave, a traveling wave, that runs along the basilar membrane, starting from the base and moving toward the apex.
And this is the genius of tonotopic organization. The wave doesn't just vibrate the whole membrane equally.
Correct. The basilar membrane is a specialized spectral analyzer. It's tuned along its length based on its mechanical properties. The membrane is naturally narrow and stiff near the base, close to the oval window. Because of these mechanical properties, this area responds maximally to, and therefore filters for, high frequencies.
And as you go up the spiral.
As the membrane approaches the apex, it gets progressively wider and less stiff, and the section responds maximally to low frequencies. So the sound frequency is encoded by the location along the basilar membrane where the traveling wave reaches its maximum amplitude.
So when I hear middle C on a piano, the maximum displacement is happening at one very precise point on that membrane, and the cells at that point are firing the strongest. And that movement causes the shearing action on the hair bundles.
Exactly. When the basilar membrane vibrates up and down, it causes a physical shift of the organ of Corti relative to the tectorial membrane, which overhangs it. This relative movement creates a mechanical shearing force that deflects the stereocilia. The OHC stereocilia are often physically embedded in that tectorial membrane, while the IHC stereocilia are deflected by the fluid flow itself. But the result is the same. The mechanical gating springs are stretched.
It's just incredible to think about the fidelity required here.
Yeah.
If the displacement needed to hear the quietest sound is less than the diameter of a single hydrogen atom, how does this mechanism overcome just ambient, random molecular noise?
That is the perfect question, and it bridges the gap between mechanics and amplification. That level of sensitivity is only possible because of two things. First, that enormous 150 millivolt electrical driving force that ensures an instant maximal chemical response.
Right, the battery.
The battery. And second, the active amplification provided by the outer hair cells, which effectively overcome the thermodynamic noise floor of the whole system.
So without them.
Without that active amplification, we would need sounds to be about 100 times louder just to hear them at all.
Mm-hmm.
To truly appreciate the fragility and the efficiency of the inner ear, we have to zoom right in on the specialized mechanical gates that are the heart of the system, the hair cell bundles. This is the moment of mechanoelectrical transduction. This is where physics becomes biology.
Okay, so let's go deep into the molecular machinery. The part that takes a movement smaller than a hydrogen atom and turns it into a neural signal.
We've established that the stereocilia are arranged in these multiple rows with graduated height. The most crucial mechanical structures connecting them are the tip links.
What are those tip links actually made of, and how do they function as a spring?
They're incredibly fine proteinaceous filaments. They're composed of proteins like cadherin 23 and protocadherin 15, and they tether the tip of a shorter stereocilium to the side of the next tallest neighbor. The tip link is the actual gating spring.
And it's fast.
It's considered one of the fastest mechanical sensors in all of biology. It's capable of responding in microseconds.
And that spring is literally connected to the ion channel gate itself.
It's hypothesized to be a direct physical connection. When the stereocilia are deflected towards the tallest row, the excitatory direction, the tip link is stretched, and it mechanically pulls open the potassium channels located right at the tips of the stereocilia. It is physical movement operating a chemical switch.
And that's where the 150 millivolt ECP comes roaring into play.
Precisely. The moment those gates open, the massive electrical pressure and the concentration gradient drive K+ ions into the cell instantly. This causes a rapid and potent depolarization.
And that depolarization travels down the cell.
It does, and it opens voltage-gated calcium channels located lower down in the basolateral membrane. The subsequent calcium influx is the final trigger. It causes the cell to release neurotransmitters, primarily glutamate, into the synapse, and that initiates the signal to cranial nerve 8.
And deflection in the opposite direction relaxes the tension on the tip links,
Which closes the channels and causes a rapid hyperpolarization or inhibition. This instantaneous mechanical gating is the bedrock of our sense of sound and our sense of balance.
Okay, so if the inner hair cells are the dedicated transmitters, why are the outer hair cells, which receive 90% of the nerve endings from the brain, why are they so vital? What is their role as a motor?
The OHCs represent an extraordinary biological innovation. They are not just passive receptors, they are active electromechanical motors. Their primary function is to actively enhance and sharpen the sensitivity of the entire cochlea. They contain a highly specialized motor protein that's embedded within their lateral membrane called prestin.
Preston, how does that work?
Prestin allows the OHCs to undergo rapid, measurable mechanical shape changes. So when the cell depolarizes from the K+ influx, prestin causes the cell to rapidly shorten and elongate. This is called electromotility. And this change happens in perfect sync with the sound frequency, up to tens of thousands of times per second.
So this physical motion, it feeds energy back into the system. This is cochlear amplification.
It is the active feedback loop, the physical shortening and elongating of the OHCs. It pushes and pulls on the basilar membrane itself. This action dramatically increases the amplitude of that traveling wave at the specific point tuned to that frequency.
By how much?
By 100-fold or even more. This active process is essential for two reasons. First, it enhances our sensitivity to soft sounds, letting us overcome that thermal noise floor. And second, it greatly sharpens the frequency tuning, which allows us to distinguish between closely spaced pitches, like in music.
So the loss of OHCs, which is common after noise damage, that's the primary cause of sensorineural hearing loss.
It is. The ear literally uses energy to actively listen better. And when that motor breaks, the sensitivity plummets.
So the mechanical signal has been converted into a chemical release, which triggers a firing of the nerves. Now that signal needs to traverse the complex pathways of the brainstem and the cortex. This is the job of the vestibulocochlear nerve, cranial nerve 8, and all its relay stations.
The central pathways are a testament to how important these senses are. The pathways for hearing, in particular, are incredibly complex. They involve crossing sides, immediate branching, multiple relay centers. It's a highly redundant system designed to protect against localized brain damage and ensure rapid processing of spatial information.
So let's start with the nerve itself, CN8. It carries the entire sensory load out of the inner ear, passing through the internal acoustic meatus right alongside the facial nerve.
And we can functionally divide the nerve based on where the cell bodies reside.
Okay, let's start with the cochlear division.
These fibers originate from the cell bodies of the spiral ganglion. These are bipolar neurons that are nestled right inside that bony modiolus. And remember the imbalance and innervation we talked about.
Right, 90 to 95% of the fibers go to the inner hair cells.
The vast majority. They're large, highly myelinated type I cells designed for rapid signal transmission, and they connect exclusively with the primary sensors, the IHCs. The remaining 5 to 10% are small, type 2 cells that connect to the OHCs. This distribution just confirms that the IHCs are the gatekeepers of all information entering the central nervous system.
And the vestibular division.
These fibers carry the balance information. They originate from the cell bodies of the vestibular, or Scarpa's, ganglion, which is located a little farther along in the internal acoustic meatus. These cells receive input from the hair cells in the utricle, saccule, and the semicircular canals, and they transmit that complex spatial data toward the brainstem's vestibular nuclei.
So the path for hearing is not direct. It's not a straight line to the brain. It involves numerous stops for processing.
This complexity ensures speed, localization, and robustness. The ascending pathway starts in the brainstem. First stop, the cochlear nuclei.
Okay.
This is the first synapse. Here, the signal immediately bifurcates. It splits into multiple streams, dorsal and ventral, which allows the auditory information to be processed in parallel across various different pathways.
Then after that,
The second stop is the superior olivary complex, or SOC. This is arguably the most critical stop after the first synapse. The SOC is the first point in the brainstem where auditory input from both ears' binaural input converges.
And that's essential for sound localization.
It is. The SOC processes the minute differences in timing and intensity of a sound reaching the left versus the right ear. But also, the SOC gives rise to those descending efferent fibers that project back to the OHCs to actively tune the cochlear amplifier.
So it's a processing center and a control center.
Exactly. From there, the signal goes up the lateral lemniscus, that's the primary ascending tract, carrying the processed signal up the brainstem to the midbrain.
Where it hits the inferior colliculus.
Right. A key relay center in the midbrain, heavily involved in auditory spatial mapping and integrating signals with the visual system.
And then?
The final stop before the cortex is the medial geniculate body, the MGB. This is the obligatory auditory relay nucleus located in the thalamus. All conscious auditory perception has to pass through the MGB.
And finally, it reaches conscious perception in the primary auditory cortex, located in Hessel's gyri of the temporal lobe.
And crucially, that tonotopic organization, that precise frequency mapping we established on the basilar membrane, is preserved all the way up to the cortex. This means specific areas of your cortex process specific pitches.
We often forget that the inner ear is a living organ, influenced by our systemic state. Our sources mention sympathetic innervation.
That's right. The inner ear receives sympathetic fibers that originate from the superior cervical ganglion, a major cluster of sympathetic nerves in the neck. These fibers don't seem to directly synapse on the hair cells, but they form this dense plexus that surrounds the labyrinthine artery and its branches.
What's the implication of that? Why is that important?
Well, the prevailing theory is that these fibers play a regulatory role. They influence local blood flow and perhaps vascular permeability within the stria vascularis.
So things like high stress or a fight or flight response, that could affect my hearing.
It suggests that systemic responses, which affect the sympathetic system, could potentially impact inner ear function via subtle changes in blood supply, or the ECP environment. While it's not fully understood, it provides a plausible biological link between systemic anxiety or vascular changes and sudden, temporary hearing or balance issues. So we've established that this is an exquisite biological system, right? It relies on precision mechanics and highly specific chemistry. Because of that, it is extremely vulnerable. And understanding the structures we just detailed is the key to understanding the so what, the common causes, and the pathology of hearing and balance disorders.
And the fundamental tragedy of the sensory hair cells is their non-regenerative nature. Once they're gone for good.
In mammals, yes. The sensory hair cells, particularly the delicate outer hair cells, are highly susceptible to damage. The most common cause is mechanical trauma from loud noise. The intense vibration causes a mechanical breakdown, specifically impacting the stereocilia and those tiny tip links, the microscopic gating springs we discussed.
And beyond mechanical stress.
They're vulnerable to infection and, critically, changes in the stability of their fluid environment.
And once they're damaged, why are they lost so quickly? Why can't they repair themselves?
Unfortunately, hair cells, unlike many other cells in the body, often undergo rapid programmed cell death apoptosis once their internal integrity is compromised. And this leads quickly to irreversible sensorineural hearing loss, or SNHL. Since the mammalian inner ear lacks the robust regenerative capacity that we see in birds or fish, the loss is permanent.
We previously touched on ototoxicity, the damage caused by toxic substances. Can we elaborate on which specific drugs cause this and why?
SNHL can be induced by a number of ototoxic drugs. As we mentioned, aminoglycoside antibiotics are notorious. Their mechanism often involves disrupting the metabolic activity of the sage stria vascularis, causing the ECP to crash. Or they may directly enter the hair cells via the open K+ channels and trigger cellular destruction. Other groups include powerful loop diuretics and specific platinum-based anti-cancer drugs, like cisplatin. And these drugs typically target the high frequency and the base of the cochlea first.
Why there?
Because that region receives the initial high concentration of the toxin as it enters the perilymph. It's the first point of contact.
And what about the loss that affects almost everyone as they age, presbycusis?
Presbycusis is the age-related decline in hearing, and it is almost invariably a type of sensorineural loss. It follows a very characteristic pattern. High frequencies are lost first, then the mid-frequencies.
And that pattern is directly linked to the tonotopic organization.
Directly. The base of the cochlea, which processes high frequencies, is the narrowest and stiffest part of the basilar membrane. It receives the most wear and tear from years and years of mechanical vibration, and it's also the first point of contact for circulating toxins. Over decades, this combined mechanical fatigue and gradual cellular loss results in reduced sensitivity, starting exactly where the mechanical strain is highest.
And genetics plays a role too.
A huge role. We should acknowledge that a substantial proportion, at least 60% of hearing loss, has a genetic basis, which can predispose individuals to early or accelerated sensory cell degeneration.
Okay, let's talk about Meniere's disease. This is the infamous condition that links both balance and hearing failure in one distressing package.
Meniere's is defined by these episodic attacks involving fluctuating hearing loss, tinnitus, which is ringing in the ears, and severe debilitating vertigo. The underlying pathology is endolymphatic hydrops,
Hydrops meaning too much fluid.
the pathological accumulation of excessive endolymphatic fluid.
So too much pressure causes temporary structural failure.
Precisely. The excess fluid volume causes the membranous labyrinth, particularly the cochlear duct and Reisner's membrane, to swell and bulge. The increased pressure mechanically compromises the delicate structures, leading to the temporary malfunction of the hair cells in both the cochlea and the vestibular apparatus.
And that's what causes the attacks.
That pressure buildup leads to the characteristic episodic attacks, the temporary hearing loss, and the explosive busyness, until the pressure is transiently relieved. The dysfunction of the endolymphatic sac, its inability to reabsorb fluid effectively, is the primary suspect in initiating this pressure problem.
Given the irreversibility of sensorineural hair cell loss, how do we treat these conditions?
Well, for mild to moderate SNHL, the standard intervention is external hearing aids. These devices simply amplify the acoustic input, taking advantage of any residual hair cell function to produce a usable signal for the brain.
But for profound loss, when the hair cells are largely non-functional, we need a technological intervention that completely bypasses that biological transducer.
And that is the cochlear implant, or CI. CIs are the greatest technological triumph in treating profound SNHL. They consist of an external microphone and processor that analyze sound, convert it into a digital electrical signal, and then transmit that signal to an electrode array that is surgically inserted into the cochlea.
And that array bypasses the damaged hair cells.
It bypasses them completely. It directly stimulates the surviving residual nerve fibers, the peripheral axons of the spiral ganglion cells, in a tonotopically organized fashion.
So the CI effectively takes over the job of the basilar membrane and the inner hair cells, electrically stimulating the neural pathway that remains functional.
Exactly. The implant uses the tonotopic map by stimulating electrodes at the base for high frequencies and electrodes at the apex for low frequencies. It creates an artificial sense of pitch based on location, just like the natural cochlea. It is a direct interface between technology and the nervous system, and it can restore a functional, if synthetic, sense of hearing.
So we started with a bone casing deep within the skull, and we ended up tracing the journey of a whisper and the path of gravity. The key takeaways from this deep dive for me are that two seemingly separate senses, balance and sound, are built upon the same fundamental hyper-efficient mechanism. It's all about these tiny, mechanically gated ion channels being yanked open by microscopic protein springs, creating an electric current based on the massive, counterintuitive potassium dynamics of the endolymph.
The sheer genius of the inner ear really lies in its redundancy and its sensitivity. The intricate spatial organization of the vestibular organs, that enormous 150 millivolt electrical driving force provided by the endocochlear potential,
The battery.
and the active mechanical amplification provided by the outer hair cells. All of it works together to create a sensory system that is unparalleled in its ability to detect the faintest vibrations. And this system is both a masterpiece of engineering and surprisingly fragile. It's susceptible to our genetics, to noise, and to pharmacological insults.
So what does this all mean for you listening? Consider this, since your entire sense of hearing and balance relies on structures that are operating at the absolute limits of physical detection, remembering that the displacement required to hear the quietest sound is less than the diameter of a single hydrogen atom.
An incredible thought.
The next time you put on noise-canceling headphones, or you choose to step away from excessive noise, you are actively protecting the incredibly delicate mechanism that determines your perception of space and reality. This astonishing system, where microscopic springs dictate your world, warrants our deepest protection.